Hello students and welcome back. Today we're going to be talking about X-ray interactions. X-ray interactions have to do with what is going on in the patient, okay? Not what's going on in the tube, but what's going on in the patient. So there's going to be some objectives for you to be able to define or explain or tell me about. So as you can see here, we talk about attenuation. We're going to talk about all the different interactions that happen within the body and the relationship with these, okay? Lot to know, lot to know. So here we go. So let's talk about attenuation first. So the definition of attenuation is the reduction in the number of X-ray photons in the beam. Okay, so the original beam, these are your incident X-rays or photons, and there you see some are being attenuated. So there's a reduction of what is in the remnant beam. The remnant beam is what is post-patient before the IR, okay? So our remnant beam, there's a reduction there, okay? Results of X-ray photons interacting with matter. So the interactions occur at the atomic level, okay? We're going to talk about what those interactions are and what happens with each interaction. So photon interactions can undergo three different processes. So they can transmit without any interaction. So you can see here's our primary X-ray photons right here. So this little guy right here is going all the way through onto our image receptor without any interaction within the body, okay? The X-ray photons also can be fully absorbed. So we look at this guy right here and this guy right here. It's not making it out of the patient and hitting the IR. So that is absorption, okay? Or they can be scattered, okay? So here they're coming in and changing direction. So any photon that changes direction is called a scattered photon, okay? So what that means is they've gone through the body and they've lost some energy. When they lose that energy, they change direction, okay? So interactions can occur with the entire atom, with the orbital electrons, or with the nucleus. So when we talk about an entire atom, we're going to tell you which interaction that is that interacts with the whole atom. When we talk about the orbital electrons, those are what we're going to talk about in diagnostic range, okay? So this entire atom is really low kVp. We see it, but it's not real predominant in diagnostic radiology, where when we talk about the orbiting electrons, the interactions with them, yes, that is us. That is X-ray. That is our kVp range. And then when we talk about the atomic nucleus, that is more radiation therapy level, okay? So when we change and hit the nucleus, then we're talking about really, really high energy, okay? So that's above our diagnostic X-ray. So the type of interaction is a function of the photon energy level, and we're going to show you how that is. All right, so low energy photons interact with the whole atom. And what that's called, the type of interaction is called coherent scattering. And remember how I told you, any incident photon or just the photon coming out of the X-ray machine, we're going to call that the incident photon. So any incident photon that changes direction is called scatter. So this is coherent scattering. So this is low energy. So we have a moderate energy photon interaction, and it has to deal with the orbiting electrons. So the two interactions, this is moderate level, has to do with diagnostic X-ray. So we're talking about photoelectric effect, and we're talking about Compton scattering. So photoelectric absorption is another name, and I'm going to explain that to you when we get to it. So the moderate level is photoelectric in Compton. The high energy, and this is typically only radiation therapy levels, is pair production and photodisintegration. So we have to touch on it, but we're not going to go real deep into them, okay? So let's look at the atomic structure. So we've covered the atomic structure in prior lectures. So the nucleus consists of nucleons. So there's protons and neutrons, and the protons are positively charged and the neutrons are neutral, right? And those are within the nucleus. Then we have these orbiting electrons. So the electrons close to the nucleus are tightly bound to the nucleus. So they're real tight. Due to its location and positive charge of the nucleus, it pulls those electrons. Remember we talked about opposites? So a positive and a negative will come together, but two of the same charge or repel. So when we have a positive and negative, that positive nucleus is keeping those electrons in the orbiting shell and keeping them close. So electrons further away are weakly attracted to the nucleus and easily removed. When they're further out, that bond pulling them together, that opposite attraction, is not as strong because they're further out. So those electrons in those orbital fields that are further out are not as tightly bound, and they're easily knocked out. Okay, so we can remove one of those electrons, and when we do that, we call that ionization. So ionization, and that's what we're working with, ionizing radiation. Okay, so we have radiation that is going to ionize. So whenever we ionize, we can cause cellular and tissue damage. Okay, so this is really important, and this is where we're going with all of these interactions, okay, because this is happening within the patient. So here, this is just a picture of our atomic structure. So we've got our neutrons and protons, right? Then around and around, so we have K, L, M, N, O, P, all the way out, and we have electrons spinning around the nucleus, and it's attracted to the nucleus because of the opposite charge. Okay. So electron binding energy, a static energy from the positive charge of the nucleus, depending upon the Z number. Okay, so the higher the Z number yields a higher binding energy. So tungsten is what we use within our tube. So with tungsten, it has atomic number of 74, and its K-shell binding energy is 69. Now, you may see in some of your textbooks it says 69.5. Okay, so it's okay. 69, 69.5, same difference, okay? We also use iodine as a contrast, and that's atomic number 53, and its K-shell binding energy is 33. So when we talk about K-shell, and we're looking at here, so here is our nucleus. This first shell is K-shell. This first one is K-shell, and it's telling you that the first K-shell binding energy is 69 or 69.5, depending on your textbook. So that's what we're going to need to remove an inner K-shell when we're using tungsten. So the inner shell electrons have higher binding energy due to its proximity to the positively charged nucleus. Makes sense. So electron kinetic energy. So dynamic energy of the electron due to its relative position in the electron orbiting cloud. Electrons in the outer shells possess higher kinetic energy but lower bonding. Okay, so electrons in the shells K, L, M have lower kinetic energy but higher binding energies. So it's opposite. Okay, they're inversely related. So as your binding energies go up, your kinetic energy goes down. Okay, so total energy of the electron is a function of combined binding and kinetic energy. So if we take a look here, this is just a cool diagram I like. So here's your nucleus, and you've got these orbiting shell electrons. Okay, so this is your K shell, this is your L shell. Okay, so if you have these same, negative, negative, positive, negative. So these electrons are drawn to the nucleus. They're being held into the nucleus right here. So they're being pulled in and keeps them in orbit as close to the nucleus. Okay, but yet all these electrons really don't like each other. So they're trying to get away from each other. So they're going to be spaced out around to give themselves some elbow room because they don't like being same charges, don't like to be by each other. So they're drawn to the nucleus, but repulsion. So we've got attraction, we've got repulsion. Okay, so they're pushing away from each other, but yet drawn into the nucleus. That's how they stay in orbit. Kind of cool, huh? Okay, so there are 5 basic interactions between X-ray and matter. So when we talk about coherent scattering, we're talking about low energy. So we already talked about that. When we talk about photoelectric absorption or effect, we're in moderate, along with Compton scattering, moderate. So the blue, moderate, green, low. Pair production and photodisintegration is high, so it's red, it's high. This is radiation therapy levels, okay? Let's talk about coherent scattering. It can also be called classical and modified, and there are Thomson and Rayleigh down here are other names, so it's got all these different names. So you've got classical and modified, Thomson, Rayleigh, and your national or state exams could list it either way, or any of these, all of these. So it's all interchangeable, okay? So these coherent scattered photons, when they interact within the body, they have no clinical value whatsoever. They do not hit the IR with any value, okay? So not diagnostically significant. Involves low energy photons, typically below 10 keV. So very, very low. Two types with same result. There's Thomson, there's Rayleigh. So Thomson is a single outer shell electron, where the Rayleigh excites the whole atom. And your RadTech Bootcamp is fantastic at showing you what each one of these interactions looks like. So with coherent, the photon absorbed by the atom. Electrons excite and vibrate the photon frequency. No electrons are ejected and no ionization takes place. So since no electrons have been ejected from the atom, no ionization takes place. It just kind of shakes up the whole cell or the whole atom, and then it spits it out in a different direction. Okay, so what happens is the energy of the wavelength of the photon going in is the same energy as the photon leaving, but it has changed direction. So instead of going straight through, it's kind of made a 10-degree bend, 20-degree bend, whatever. Okay, so the atom stabilizes itself by releasing a photon of equal in energy to the incident photon, but in a different direction. So it's considered scattered since it changed direction. So the quality of coherent scatter on patient dose, so no energy absorbed, no ionization, therefore no biological change or harm. Awesome. Scatters in a forward direction, so typically it doesn't affect us technologists with getting dose from the patient. And with our image quality, unfortunately, this scatter does hit the image receptor sometimes. Most of the time it's just absorbed in the body. It's considered just dose. But when it does make it out of the patient, it will hit the IR and decrease our contrast and increase our noise. So noise is anything unwanted or a misrepresentation of the anatomy. Okay, we consider that noise. So it decreases contrast and adds noise to our image. So it does have negative effects, but it's pretty small. So the key takeaway is not a big concern for radiography. It happens with low kVp, has no effective patient dose, and doesn't expose the technologist, but it does create noise and decrease our image contrast. There's really not much that we can do about it. It is what it is. So here we've got decreased photon energy. We have increased scatter. So if we take and we're shooting a hand, and instead of shooting at 50 or 60 kVp, we shoot it at like 40. Okay, so we're going to have a lot more coherent scatter, which is going to reduce our contrast. Okay. All right, so here is Thomson scattering, which is a form of coherent scattering. And you can see our incident photon coming in and interacting with an outer shell electron, and it changes direction. So it doesn't ionize, it doesn't remove it, it just kind of interacts with it and then spits out a photon in a different direction. So that's called Thomson. Then we have classical scattering. It's called Rayleigh or unmodified. So an incident comes in, the whole atom, see right here, the whole atom gets affected, and then it spits out a scattered photon in a different direction. No removal of an electron, there's no ionization, and it's very low kVp. All right, so now let's go into photoelectric absorption. Now, we deal with photoelectric absorption and Compton. So those are the two that we're dealing with in diagnostic range all the time. So with photoelectric absorption or effect, Bouchon calls it photoelectric effect. I call it photoelectric absorption according to the other textbooks. So when we're dealing with photoelectric effect, we get an ion pair formed when an electron is ejected from the atom, becomes known as a photoelectron. And I'm going to show you a diagram that's going to help you with this, but I want to run it by you first. The remaining atom has a vacancy in its inner shell. The incident photon energy completely absorbed by the inner shell electron. So most likely to occur when the X-ray photon has just slightly more than the energy of the binding of a K or L shell electron. So that's why it was so important. The metals in which we use from inside the tube on the lecture that you got there, we use a lot of tungsten. Tungsten is 69 or 69.5, right? So that's what we're looking at. So looking here, here's a good diagram. Incident photon interacts with an inner shell orbital K or L electron, giving all of its energy to the electron. So it's completely absorbed, okay? And it ejects it from orbit. The photon is absorbed, so really important. The ejected electron, the photoelectron, imparts the atom with energy equal to the excess of the electron's binding energy. So here's right here, so ejected electron, or what we call a photoelectron. So this is called photoelectric effect or absorption. Now, when I call it absorption, I'm doing it for a reason. So this is photoelectric absorption. It's being absorbed by a K or L shell. So here's K, L, M. So here K typically happens in K shell. So K shell is being fully absorbed. Then it like spits out this photoelectron. So photo from your photoelectric effect here, here's your photoelectron. So photon in, electron out. Okay? So there's a vacancy in the inner shell, K or L, that must be filled. One of the electrons from the outer shell, usually in the next orbit, will drop down to fill the void. Now, you remember from the interactions within the tube, if we knock out an inner shell electron and there's a vacancy, the atom is completely unstable and it's going to immediately try to stabilize itself. And it's going to drop down an electron from an outer shell into the inner shell. So when it does that, it's called characteristic cascade. And when it drops down, it's going to release the difference in the binding energies in the form of a photon. Okay, so as the electron drops to the void, it may shed its excess energy as a secondary photon. So it has secondary photons that is the binding energy difference between the L and the K shell. Okay, does that make sense? So photoelectric effect or photoelectric absorption, incident photon comes in, completely absorbed by a K or L shell, typically K, absorbed completely. It spits out this photoelectron, so photon in, electron out, and then we have the characteristic cascade with secondary photons at the energy level of the binding energy difference between the two. All right. So photoelectron energy can be determined with the following equation. So if you take the incident is equal to the binding and the kinetic energy. You add those two together and you get your incident. So no energy is lost. Okay, it's only converted. So photoelectron characteristics. So we take a look at the kinetic energy, and these typically on these photoelectrons, so that electron that got spit out of the K shell, it's usually reabsorbed quickly within 1 to 2 millimeters of tissue. Okay, so they don't penetrate very far. So a lot of them are dose. Okay, dose. So an ionized atom Inner shell electron vacancy makes the atom electrically unstable. So we get that characteristic effect. So that cascade, okay? The vacancy filled by an outer shell electron, the electron undergoes change in energy level, so it emits a characteristic photon. The energy of the photon determined by the difference in the binding energy. So here is a good view of it. So we've got your incident photon. Typically this is a wave, right? So we got a wave coming in, it hits the K shell, knocks it out. So we have a photoelectron over here, right? So photon in, and we've got a photon out. So this is wrong. This is a photon, right? This is not an incident electron. So interesting. Maybe they're referring to this being the electron. That's a good head scratcher, right? Okay, so then it drops from the L shell down to the K shell. It's going to give off the difference in the binding energy for the K shell. And then same thing here. If we go from M to L, it's going to give off a photon. Okay, so each time these are called secondary characteristic photons. All right. Qualities of a photoelectric effect, okay? So we've got ionization, where coherent, we did not have ionization. We have ionization now, okay? So we have a free electron that damages cells and tissues. It's 100% patient dose, okay? So these are being absorbed in the body. So they're not making it out of the body. So all of these photons are contributing to patient dose, which causes cellular and tissue changes, okay, or damages, okay? Image quality, super important that we have this. So the image quality creates contrast by being absorbed. So when we're looking at an X-ray and we have black and white, the white is what is completely absorbed. The black is what has been transmitted. So when we're looking at the differential absorption, so what has passed through the patient versus what is still within the patient, what the density is within the patient, okay? So the bone is going to absorb more photons than the lungs, right? So this photoelectric absorption or effect is super important, okay? We must see the differences between the black and the white. So the black is something that is more radiolucent, where the white is something that is dense and not radiolucent, okay? So it shows us the white on the image, which is a good thing. We need that. So photoelectric effect or absorption is dependent on the thickness of the part. So thicker the anatomy, more absorption. Thinner the anatomy, less absorption. The density of the tissue. So is it fat versus muscle? So the more dense, more absorption, less dense, less absorption. Atomic number. Low atomic number, less absorption. Higher atomic number, so such as calcium or iodine, more absorption, okay? KVP, low KVP, more absorption, as it has less energy to penetrate the part. Where if we have high KVP, there's less absorption as it has more energy to get through the part, okay? So KVP plays a big role with our photoelectric absorption. So if we're trying to get through, let's just say, my brain went dead. If we're trying to get through a lumbar spine, let's just say, and we're using 40 kVp. So what's going to happen is the kVp, the energy of the photon, is not going to be high enough to make it through the bone and onto your IR. Where if you take it and you bring it up to 90 kVp or 100 kVp, which is really high for a lumbar spine, it's going to all pass through. So we have to find a medium. So we're going to give you kVp ranges that you need to know so that you don't, one, underpenetrate and have photoelectric effect for all your photons where none of them hit your IR, or you have too high of kVp where everything passes through the part and doesn't give you any black and white. You need some absorption, okay? So you got to find a happy medium based on the based on the atomic number, the density of the tissue, and the thickness of the part. So you're going to learn about that as we go through this program. So photoelectric. If you decrease your kVp, you're going to increase your photoelectric absorption and you're going to increase your contrast. So when we say increase your contrast, what I mean here, we have high contrast, low contrast. So if you have high contrast from a low kVp. So there's not enough energy for those photons, okay? You're going to have absorption or transmission, one or the other. So you're going to have a lot more black and white. You're not going to have shades of gray. So you can see here, I can see the ribs really well. I can see the nodule there really well. Compared to here, it's just black and white. There's no shades of gray. Okay, so with low kVp, you get high contrast. And you're being absorbed here. So you can see here, hard to see this, the T-spine through there. This is low contrast and it's giving you lots of shades of gray. All right, so we talked about coherent, we talked about photoelectric absorption or effect, and now we're going to talk about Compton. So Compton, scatter. So Compton is a bear. Compton is something that we're dealing with, and it just really doesn't do us a whole lot of good. Where photoelectric does. Photoelectric is important. We need to see the black and white, right? Compton here, the incident photon interacts with an outer shell electron and ejects it. So when it's ejected, it's called ionization. And when it ejects it out, that ejected electron is called a Compton electron. Okay, so when we talked about photoelectric effect or absorption, it was a photoelectron. So now we're dealing with a Compton electron. Okay, so that electron that's been thrown out of there is a Compton. So scattered photon redirected at some angle with loss of kinetic energy. So when we lose kinetic energy, we can't get rid of energy, so we have to convert it to something, okay? So we're going to take that and it's going to give us a photon, okay? Has lower energy than the incident photon and goes in a different direction of the incident photon. So results in a Compton electron and a scattered photon. So I'm going to show you a diagram and that's going to make more sense, but I want to talk to you about it first a little bit. So you have this photon that's coming in and it's going to hit an outer shell, right? Outer shell electron that has high kinetic energy and low binding. So it's going to take that electron, it's going to knock it out, and it's going to be a Compton electron now. Now it's going to knock it out into a different direction, okay? So it's not going to go just straight ahead. Typically it's changing direction. And it's going to, the difference in the deflection from the incident to the way that it's going is going to determine the wavelength of your scattered photon. Okay, so when you have an incoming photon, it hits an outer shell electron, knocks it out, so you have a Compton electron and you get a scattered photon also. Okay. Energy transferred to recoil electron, they also call it a recoil electron. The Compton electron is also recoil. Okay, so interchangeable. It affects the angle and the energy of the scattered photon. So lower frequency and increased wavelength of a scattered photon. So recoil electron behaves as a free electron. So this free electron will go on and on and on and keep having interactions and filling shells. So if there's a vacancy in like an M shell from a photoelectric, it may just jump into that shell depending on the energy. So this is millions of them are happening at the same time, okay? So this isn't just like one crazy, free electron, Compton electron or recoil electron. There's millions of them. So all this is happening within a millimeter of a second. Millisecond, something like that. Okay, so Compton scatter, the recoil electron travels it until it fills a vacancy of another atom. The scattered photon continues to interact until absorbed photoelectrically or exits the patient and exposes us as radiation workers. So Compton scatter can be any angle. So if it's no 0 degree angle, means no transfer of energy to the scattered photon. So there you go. So there's no scattered photon, right? We didn't change direction. You have to change direction in order to be scattered. So as it increases to 180 degrees, more energy is transferred to the Compton electron. At 180 degrees, Compton scatter is still 2/3 of its original energy. So as we change in our degrees, it's changing the energy level of our photon, okay? Backscatter radiation. So backscatter is considered scattered that is coming back to the same direction as the incident. So as the incident comes in, it's coming right back in the same path as the incident. That's called backscatter radiation. Qualities of Compton. So we have patient dose. It has ionization. So photoelectric absorption and Compton both have ionization. So a free electron causes cell and tissue damage. Yep. There's occupational dose. So this is the only one that radiates us as occupational workers. So that's where we get our dose from, is from Compton scatter. So the scatter gets the technologist. This is where the technologists get all their dose. So when we have a read on our badge, it's from Compton scatter. Image quality. Scatter photons cause noise on our IR, okay? So when they pass through, they're coming out at an angle, okay? So they're not representing the anatomy in which they're interacting with. So it's not going straight down to show the spine. It's actually taking the spine and putting it over by where the kidney is. So we call that noise. So it's something unwanted on our IR. It's a misrepresentation of the true anatomy, okay? It also decreases contrast due to scattered photons. So it's decreasing our contrast. So instead of it being black and white, it's giving us all these shades of gray. But these shades of gray are not true representation of what it should look like, okay? So Compton is dependent upon part thickness, so more matter, more scatter. So part density, more scatter. Field size, so it's really important to collimate. So more matter, more scatter. So if you open up your collimation and make it bigger, you're getting more matter within there, okay? Matter, we're talking about patient, okay? Increasing KVP, so higher KVP equals higher scatter. Okay, so we want a high KVP so we have less photoelectric absorption, which is direct patient dose. But we can't have too high because our whole image is going to be just this gray blob from all of the scatter on it. Okay, so we have to find the happy medium with our KVP. How to reduce scatter with Compton. So if we reduce Compton scatter, we reduce part thickness, we reduce field size, and reduce our KVP. So our images will look pretty. So Compton scatter happens with all energy ranges. So mainly at higher energy ranges though. So typically when we're higher energy is when we're going to see more Compton scatter. Okay. So let's take a look at what it looks like. So we have one, this is our incident photon, right? So the photon interacts with the outer orbital electron, imparting some of its energy to the electron, injecting it from orbit. So what's this thing called? Remember this? It's called a Compton electron or a recoil electron. It can be either name, okay? So the ejected electron, the Compton electron, leaves the atom with an energy equal to the excess imparted by the photon. So here we've got number 3 right here. The photon continues in an altered path, scattered, with less energy, so a longer wavelength. See how high energy this is, and see how long this wavelength is, which means it's lower energy. So you can see we had some energy loss, but if you add these up, it'll equal here. Because remember, we can't get rid of energy, it's only converted. So when we're talking about a Compton effect or Compton scatter, here's your incoming photon, hits an outer shell electron, knocks it out, so we get a Compton electron or a recoil electron, and then we have a lower energy scatter photon. So you can see here we've lost energy and we've changed directions. All right, so Compton scatter is the source of occupational exposure and radiation fog, what we call fog or noise on our IR. Most scatter travels in a forward direction. but there's also the backscatter. So the backscatter, you see here's your incident photon. It would come right back over here. Okay, so come right back on top of where the incident came in. So as you can see here, we have our 0 degrees right here. So nothing, okay? And you can see here all of our different angles, okay? And you can see how our dose is. So all in through here is really high dose, okay? So just changing direction just a little bit, okay? So angle of scattering in degrees. All right, so I like giving you guys visuals. When we have a patient, typically we have a shield put up, but just so you know, it's coming out of the patient in all directions, all directions. All right, let's go into pair production. Now, pair production, this is the start of our radiation therapy levels, okay? So this is not what we find in diagnostic X-ray. So pair production, the incident photon energy level required is a minimum of 1.02 MeV. Now in X-ray, we deal with KeV, right? Kilo electron volts. This is mega electron volts, okay? We use this a lot in PET scanning when we're doing PET scans for where we inject a radioisotope and then we put them under gamma camera. And, so it's out of our diagnostic X-ray range. So what happens is the nucleus absorbs the incident photon. The incident photon loses all energy, results in a pair of electrons. So there's a negatron and a positron. The negatron is absorbed by the nearby atom. Common in nature and quick to react, the positron combines with another negatron. And they have this annihilation reaction, okay? And the matter is converted back into energy. So, does not occur in diagnostic range, utilized in PET scanning. It's more significant in radiation therapy and not significant interaction until energies reach 10 MeV. Okay? Important that you know that. Then we have photodisintegration. So it's extremely high photon energy. It's 10 MeV or greater. Absorption of the photon by the nucleus. The excited nucleus takes in this energy and then spits out this alpha particle. Okay, an alpha particle is bad. So it's not significant in diagnostic range. So photodisintegration, really high energy photon, 10 MeV or greater. The nucleus absorbs this and spits out an alpha particle. Okay, that's what you need to know. All right, so effects on technical factor selection. So most of the X-ray beam is attenuated while some of the beam is transmitted. So we need both. As KVP increases, the number of photons transmitted without interaction increase. So you're going to read that in Bushong. You're going to say, wait, what? I thought we had some Compton. I thought, so as KVP increases, the number of photons transmitted without interactions increase. So we're going to get to where there's a certain KVP value for the body. Okay, there's a max. Typically, we don't go above 125 KVP because everything is transmitted. There's no photoelectric absorption happening at that point. Okay, so as we increase our KVP, the number of transmitted photons without interaction increases. Okay, so we want to find that happy medium. So decreased probability of photoelectric and Compton interactions. So the inverse is also true. So if you take your KVP and you decrease it really far down, so you take it instead of 125, you're going to shoot it at 40 KVP. Okay, we don't shoot anything at 40, but if we were to shoot it at 40, we're going to have a lot of photoelectric absorption and very few Compton interactions. Okay? So, photoelectric versus Compton. So, highly dependent upon two key factors. So, the incident photon energy. So, remember we talked about the 69, 69.5. Also, the Z number of the target atom. So, really important if you know that you're using tungsten or you're using molybdenum if you're in mammography. So the Z number of your target is going to change what the binding energies are for that element. Oh, so photoelectric is predominant interaction in higher Z number materials. So Compton is predominant in soft tissues. Effects on technical factors. So with attenuated beam, as KVP increases, photoelectric absorption decreases and Compton increases. So higher the KVP, we're going to have less photoelectric, we're going to have more Compton. Okay? Increases percent of scatter and decreases percent of absorption. So when we take that KVP and we raise it up, we are also raising the amount of scatter that we're going to be getting. And what that does is it degrades our image. So really important. So Compton scatter typically predominates with diagnostic X-ray range. And photoelectric interactions predominant in two circumstances with lower energy ranges, so 25 to 45 keV, produced by 40 to 70 techniques. So as you learn and go through this, 30 to 40% of the chosen KVP, the average is 30 to 40% of that. Okay, so if you take this 30 to 40%, you're right at 40 to 70 kVps. You're going to cover that in your emissions portion, okay? And photoelectric in elements with a higher Z number, okay? So 40 to 70, you're going to predominantly have a higher photoelectric range, okay? All right. Introduction of contrast agents results in increased photoelectric absorption. So you have a higher Z number, okay? So the higher the Z number, the more dense that is, therefore you're going to have more absorption. So when photoelectric absorption predominates, results in an image will have higher contrast, clearly seen with film screen imaging, so way back in the dark ages when we used film screen. It's not so obvious with digital. That's why I brought it up. So we kind of still teach on old school methods. We can window and make things look pretty. So we will refer to film screen every so often just so that you can get your bearings. So with digital, we're able to window and get the image to look the way we want it to look. So low KVP and high mass also will. So that low KVP, which is a lower energy photon, which is going to predominate with our photoelectric absorption, okay? So photoelectric results in increased patient exposure, not just exposure, but dose. When Compton interactions predominate, results in images will have lower contrast, clearly seen with film screen, but not so obvious with digital. Here we go again, right? So high KVP and low mass produce more Compton interactions, but less patient exposure or dose. Oh, so there's got to be a happy medium in there, right? So digital processing can compensate for loss of image contrast to a degree. So we can take it and we can window it and try to make it look pretty. All right. Let's wrap it up. So, what do we see here? What do you think A is? What do you think B is? These are two different interactions. I'll give you a hint. They're in the moderate range. They're the two most popular in diagnostic imaging. So we have an incoming photon, and it goes to an inner shell, and it's kicked out our photoelectron, versus an incoming photon hitting an outer shell, knocking out a recoil or Compton electron, and then we have this scattered photon coming out. Okay, so we have an inner shell and we have an outer shell. You ready? Here we go. A, we have our inner shell, or our photon coming in, hitting the inner shell. We have our ejected electron, so our photoelectron. So you can see here, we have cascade that would happen here. So this is, right here's our cascade. This is photoelectric effect or absorption, okay? Where B, this is Compton. So we've got our incoming photon, and we've got our outer shell being knocked out to our recoil or Compton electron, then we've got our scattered photon coming down. Okay, now I'm going to tell you a trick on getting to know the difference between the two. So you're looking at these and they look just like the interactions that happen in the tube, right? So if you're looking at this and you're going, oh my gosh, is this, is this characteristic? What is this? Is this Bremsstrahlung? What is this? If you look and this says photon, you know that this is in the patient. Now if this says electron, incoming electron, then you know that this is in the tube. Okay, so photon is in the patient, electron is in the tube. So this, if this said electron, this would be characteristic, right? Characteristic. And if it comes in, it has the incoming, but it doesn't interact and just kind of changes direction, but the wavelengths stay the same, and this says electron, what would that be? What would that be? That would be Bremsstrahlung, right? And if it's a photon, that would be coherent. So coherent, if it doesn't interact with anything but changes direction. If it's photon, it is coherent. If it says electron, then it is Bremsstrahlung. So if it says photon, then you know it's in the patient. And in the patient, we've got photoelectric absorption or effect, or we have Compton. Okay, then we have coherent, which is really low. All right, I hope all of this made sense. You may need to watch this a couple times. This is very important, okay? Very important that you guys learn this stuff. Watch their Rad Tech Boot Camp. It is fantastic. Make slides, flashcards, do whatever you need to do to make sure you know this information really, really well. Thank you and enjoy.